Okay, now we get on to question number 9. Question number 9, we've got a plane flying in a circle around a point A, and it's flying at a certain speed. Then, for this question, there's also a rocket fired from the center, and this rocket follows a path and eventually collides with the plane. And we want to know, and the path that the rocket follows is as such: at every single point, let's say at this point here, the plane, the rocket, and the center are collinear, in other words, a straight line. And at every single point, the rocket is flying at the same speed as the plane. And the question is, how long does it take for the rocket to collide with the plane? Okay, so one way to try and solve this question is you start with the properties. So it's collinear. Is it a double? Collinear. And it's the same speed. And then you use direct reasoning, and eventually you'll get that the collision time is equal to something. There are other ways to try and solve this, and let's look at that. Now, one of you guessed that the path that the rocket would take would be a semicircle. So what you could try and do is you could try and prove that if the rocket and the plane are always collinear, and if they have the same speed, then this implies that the rocket takes a semicircle path. Okay. Now, and then from that you can work out what is the collision time. This will still be difficult. So what you could do instead, well, not instead, but to do this like this will be difficult. So you could try and solve a different problem. This is the proper way to do it. But another way to just like sort of check whether you are on the right path is, instead of showing that this and this implies that, you could show that if they are collinear and the rocket takes a semicircle path, then they'll be flying in the same speed. Note that this is a very different statement from that, but this is easier to prove and also would show that you are going in the correct direction in your proof. Now, to say that they're always the same speed is equivalent to saying that they travel the same distance at all times. Now let's start with the problem. So let's say this is following a semicircle's path and it's anywhere on the path over here. Let's say this is following this curve and it's anywhere on this curve, and let's say that they are collinear, then what I need to do is I need to show that this distance is the same as that distance over there. Okay, I'm actually assuming that it starts at the top over here, but what you could do is you could work out this total distance over here, where it ends, and then you can work out that exact same distance on this bigger circle, and you could see that it will be at this point. So in other words, when the rocket's here, the plane must be there if this is going to work at all. Now to calculate this distance, I need, well, I don't need, but I could use this angle over here and the radius. Basically, the distance, let's call this D1 and let's call this D2. And let's just call this for temporarily angle θ1. The distance is equal to the radius times by θ1 times by some constant, where that constant is actually 2 pi divided by 360. But this is just the constant that's going to disappear later on. Then to calculate this distance, I can also construct two lines to the center of the semicircle, and that distance will be the same constant times by the radius of the little circle, let's call it R2, times by this angle over here, like that. And I just have to prove that this is equal to that, which is the same as proving that R1 θ1 is equal to R2 θ2. And we know that the radius of the little circle is half of the radius of the big circle. So I can substitute that in, and I can cancel that with that. I can take the 2 to the other side. So all I have to do is prove that 2 θ1 is equal to θ2. So I need to prove that 2 times this angle is equal to that angle. Okay, this diagram has gotten messy, so let's redraw it. Here we've got the angle θ. Okay, let's just say θ1. This is the vertical position, so this is 90 degrees. So this angle over here will be 90 degrees minus θ1. Then I can draw in this radius from that to the center of the circle. This radius is equal to that radius, so therefore this angle over here is also 90 degrees minus θ1. And then I can work out that angle, which is just going to be 180 degrees minus these two, which is 2 times by θ1 as we required. So I started off with the fact that they are collinear and they are semicircle. Now I started off with this angle, θ1. I went and calculated this angle, which is 2 θ1. Then from those two, I could just work out these two distances. They will both be the same distance, and therefore the plane and the rocket are traveling at the same speed. We have proven that this implies that. And at first I thought that proving that this implies that would be a lot easier than proving this, but I was wrong. In fact, well, sort of wrong. In fact, it's an infinite times more easier, because this statement over here is false. Okay? If you're to work out every single possible way that the rocket can be collinear with the plane and can travel at the same speed, you'll find out that there are other paths that the rocket can take. You see, at any given point in time, let's say at this point, what the rocket can do is it can just do a sharp turn and travel back through another semicircle that goes through these 2 points, and that would go to the outside of the circle. And for this part, it will stay collinear with the outside plane up to that point, and as it's traveling down here, it will stay collinear with the plane. And then from this point, it can do the same thing. It can travel in a semicircle outwards. It might travel all the way to the side and then collide with the plane there. But there are an infinite number of possibilities. And because it can stop at different points, if it stops here, then this portion is going to be a lot shorter where it goes back to the base, so it will line up with the plane at a different point, and then it'll only fly outwards. It could be traveling back, and then it could all of a sudden decide to travel outwards. There's just an infinite number of possibilities, and basically it can take any time to reach the plane that is equal to or longer than that number you found. And I don't even know if that number you found is the actual shortest time it takes for it to collide with the plane. If you want a very interesting path they can follow, interesting path is this one. So interesting, I find it a little bit funny. What it could do is, instead of going around this way, as the plane is flying here, it can go the mirror image at the back, and if this point is always collinear with the plane, then this point in the mirror image will also always be collinear with the plane. Then once it gets here, it can fly any length along the border, and because it's the mirror image, it will stay that length away from the plane. Then from here, it can fly in a semicircle back to the center, and then it can fly in, let's see, the plane will be 90 degrees further. Then it can fly in a semicircle outwards so that it meets the plane at that point. So I just find it like kind of funny that there's a solution with the rocket flying along the perimeter of the circle, kind of chasing the plane, and then it flies back in the middle and then flies out again to meet the rocket.